Hello AP Chemists! In today's video, we are going to talk about thermodynamic favorability. So that's thermodynamic favorability. And what I mean by that is the production of products, so is the formation of products favored at a particular temperature? Or in other words, does it happen? We are going to use a tool called Gibbs free energy to determine that. And Gibbs free energy is designated with a capital letter G. Free energy is defined as the amount of energy that is available to do work. So having free energy and tracking the free energy in a reaction is going to help us determine whether a reaction would happen or not. So this says that the change in free energy, or delta G, because remember delta means change, is a measure of the thermodynamic favorability of a reaction. So if we calculate this and we find that delta G is negative, then we say that the process is favorable. So for a reaction to favor the formation of products, delta G needs to be negative. When delta G is positive, we say that the reaction is not thermodynamically favorable. So when it is positive, the reaction is not thermodynamically favorable. The following equation is called the Gibbs-Helmholtz free energy equation, and it's what we're typically going to use to determine if a reaction is thermodynamically favorable or not. So one thing that you'll notice here is we have some of our old players, right? We've already talked about this. That is enthalpy, where we are tracking the heat that is being transferred in a reaction. We also have delta S, which we talked about most recently, and that is the entropy or disorder, dispersal, randomness in a system. So both of those things are going to have an effect on the thermodynamic favorability of the reaction. You'll also see this guy here. We know him. Okay, that is going to be our temperature. So obviously temperature also plays an effect, or also affects whether a reaction would happen or not. There are some points that I do want to make about this equation. One is that reactants and products must be in their standard states at 1 atmosphere, and the solution must be at 1 molar concentration. The temperature varies, but it is often at 298 Kelvin, which is 25 degrees Celsius. Entropy values are typically given in joules, while enthalpy values are typically given in kilojoules. That is one of the biggest mistakes that I see with one of these problems. You have to make sure that these units match up because we are subtracting in this problem. And when you subtract units or add units, the unit has to match. So make sure that you convert one unit to the other. Make sure that you convert one unit to the other. Okay, that's my way of getting your attention because that's super duper important, right? So like I said, that is a huge error that students tend to make. The temperature that we are going to use is going to be in Kelvin because we want to make sure that we have an absolute temperature scale where there are no negative values. So if you are given a temperature in degrees Celsius, which often happens, you need to convert it to Kelvin first. To find our Kelvin temperature, you are going to take the temperature in degrees Celsius and add 273. It's actually 273.15, but the AP test, this is a given value, this is a given formula in your formula chart, and that is that the degree Celsius plus 273 would give us our temperature in Kelvin. So remember, we're looking for a process where delta G is negative because those processes are thermodynamically favorable. We can use the Gibbs energy equation to think about this conceptually or qualitatively before we ever look at numbers. Okay, so I can figure out by looking at this equation and how delta H and delta S affect delta G. Another point that I want to make is that even though a reaction may be thermodynamically favorable, it may not occur at a fast rate due to a high activation energy. This is a concept that we will talk more about in our kinetics unit, but realize that something can be favorable and maybe just doesn't happen because it has a big, large bump in its reaction profile, and we have to add energy or some kind of spark to make it happen. Okay, this next part is where I'm going to show what I mean by we can use this equation to talk about the favorability and predict the favorability of a reaction. Case 1, I have that delta H is negative. We've talked about what that means. That means that we have an exothermic reaction. And that delta S is positive, which means that we are going to have more disorder or more entropy. One thing that you'll notice is that reactions that are exothermic and go towards greater disorder are always going to be favorable. Okay? Now, reasoning, if we think about an exothermic reaction, if we have high energy in the reactants, by the time we get to our products, we're going to have lower energy. That's a release of energy. Remember that nature is always going to the lowest energy state. So exothermic reactions accomplish that, making that a more favorable reaction. Having a positive delta S is also going to make a reaction more favorable. Okay, you can think about that if we're increasing our disorder, then we're going to make, if disorder is increased in our products, then a reaction is going to be more favorable. Think about the second law of thermodynamics there, which says that going towards greater disorder in the universe is always going to be favored. Okay, now actually looking at this, if I kind of do the algebra and I plug in a negative delta H, that makes delta G more negative. And we can see that algebraically here. If my delta S is positive, since I'm subtracting a positive number, that also makes my delta G negative. So in this case of a negative delta H and positive delta S, my delta G is always negative. Okay, which means that in this case, these are always going to be favorable. I'm just going to say thermodynamically favorable. Okay, that does not mean what you think it means. It means thermodynamically favorable. Don't get cute. Okay, for case 2, we have that delta H is negative, which we said is going to increase our favorability. And delta S is negative, which is not. So here we have a different situation. One thing makes the reaction favorable, the other doesn't, right? And so we have to see, like, when would this happen? When they're both the same sign and one contributes to favorability and one goes against it, these are going to be called temperature-dependent reactions. Oh, that was a T. So those are going to be called temperature-dependent reactions, meaning that it depends on the temperature or what temperature the reaction is taking place at. So in this case, we know that delta H is going to make delta G more negative. But delta S, since we are subtracting a negative, that makes delta G more positive. Okay, so we want this to be minimized in order to have a thermodynamically favorable process. So this is favorable only at low temperatures. And I usually try to think of this as negative, negative, low. Okay, negative, negative, low. For the next one, we have positive and positive. Okay, so we have an endothermic reaction. That's not favorable, but it goes towards more disorder. So we want this factor here to be maximized. To get that to be maximized, we're gonna have to be at high temperatures. So once again, case 3 is temperature dependent, okay? And it would be favorable only at high temperatures. Okay, so I like to think of that as positive, positive, high, negative, negative, low, and then when it's negative, positive, it always happens. Okay, the last situation is two unfavorable things happening. Both factors are unfavorable or not favorable. So this is not favorable at any temperature. So endothermic reactions that get more ordered are never going to be favorable, okay? So summarizing the signs, okay? What's your sign? Okay, when we have a negative and a negative delta H and a positive delta S, this is always favorable. Okay, so that's always thermodynamically favorable. If I have a positive delta H and a negative delta S, this is never thermodynamically favorable. When I have a negative and negative, this is thermodynamically favorable at low temperatures. And I would also say that the thing that would make this favorable is the enthalpy. So this is enthalpy driven. And then these would be thermodynamically favorable at high temperatures, and it would be entropy driven. Okay, so entropy makes it happen, or enthalpy makes the reaction happen, or makes it favorable overall. Okay, we can do some calculations, and we can do calculations using the Gibbs-Helmholtz formula or equation that we just looked at. We also have this other equation that we can use that looks a lot like our delta H of formation formula, and really we treat it the exact same way, including that if elements are in their standard states, we would treat them as 0. So same rules as when we did delta H of formation problems. So let's look at a couple of examples here, and we'll look at several more in class. So it says to find the delta G for a reaction if delta H is negative 237 kilojoules and delta S is negative 642 joules per Kelvin. Is the reaction thermodynamically favorable? So we're given a delta H and we're given a delta S. So I'm going to use my Gibbs formula, okay, which looks like this. Now remember that I have to make sure that these have the same units, and they don't. I don't care if you make your delta H into joules or you make your delta S into kilojoules. Just make sure that their units end up matching. So I'm going to convert my delta S to kilojoules. That's typically the way that you're going to see it happen more often. So most of you probably could just do it in your head, but there are 1,000 joules in a kilojoule, so that's negative 0.642 kilojoules is per or over Kelvin, would be my units for delta S. So I'm going to plug everything in. Oh, I never gave a temperature. Oh no. How sad. Okay, let's say that this is at 25 degrees Celsius. I'm making that up. Okay, so let's imagine that the problem said that it is at 25 degrees Celsius. So that would be 298 Kelvin. So I added 273 to that. And then that's negative 0.642 joules over Kelvin. So Kelvin cancels. So that's negative 237 minus 298 times negative 0.642. Okay, and I got that my delta G is negative 45.7 kilojoules. Okay, the reaction is thermodynamically favorable because delta G is negative. Okay, and I'm just going to add here, didn't really ask for this, but if it did, I would say that this is enthalpy driven because the enthalpy is what made delta G negative, whereas the entropy made it positive. Okay? So the next question, it says, is this thermodynamically favorable? We're really following the same process. Once again, I'm going to say it's 25 degrees Celsius. I don't know why I decided not to include that again. But let's go through the problem. So we have a delta H. Our delta H is negative 163 kilojoules. I said that our temperature is 25 degrees Celsius, which is 298 Kelvin. And our delta S, we need to make sure it's in the right units. I'm going to say 0.148 kilojoules over Kelvin. So I'm going to put that into my calculator. And I got that delta G is negative 207 kilojoules. So I would say that the reaction is thermodynamically favorable because delta G is negative. And in this case, it's both entropy and enthalpy driven. Okay, remember that this one would be at all temperatures, it would be thermodynamically favorable. Okay, and that's what I would expect, right? Because it's a negative delta H and a positive delta S. Let's look at one more question. So let's look at one more question, and then we'll look at some more in class together. So here I give you a delta H, I give you delta G of formations of Fe2O3 and Al2O3, and I ask you to calculate the delta S for this reaction given the data. And once again, I need to say that this is at 25 degrees Celsius, okay? And I also didn't give myself a lot of room here, so kind of bear with me. To solve for delta G, I'm going to use this formula. So I'm not going to rewrite it because I don't have a whole lot of room. So I'm going to use my products minus reactants formula. Now remember that aluminum would be 0 and iron would be 0 because those are elements in their standard state. So make sure that you do keep that in mind. And once again, we're going to do products minus reactants. Al2O3 is negative 1582. Reactants, we have Fe2O3, which is negative 740. And we have aluminum, which would be 0. Okay, I got that my delta G for this reaction is negative 842 kilojoules. At that point, I'm going to use this formula to solve for delta S. So we know delta G. Delta H was given to us in the problem. I told you that the temperature is 25 degrees Celsius or 298 Kelvin. And we are solving for delta S. So I'm going to do negative 842 plus 850, so that's 8. And I'm going to divide that by negative 298. Yeah. And I got that delta S is negative 0.0268. Now looking at that, I have to remind myself and remember here that this would be in kilojoules over Kelvin. Okay, since we were looking at things in kilojoules. So if it were to ask for it in joules, because that typically is how you see it, then you would make sure to move the decimal, and that would be negative 26.8 joules over Kelvin. Okay. So hopefully that's a good introduction for you. We will look more in depth in class, and also we're going to do a lab with this. All right. Bye, y'all.